Okay, let me first write the answer for this question. Okay, this A vector is 2 meters in the x direction plus 3 meters in the y direction.
It's not me, it's somebody else with like 2 meters in I direction.
2 meters in I direction plus 3 meters in j direction. This is also fine. A is not equal to 2x plus 3y. A is equal to 2x plus 3y meters. That's fine. All these three are fine. This one is not fine. A is not equal to 2 meters plus 3 meters. A is not equal to 2 meters plus 3 meters. These are wrong answers. Because here you forget the vector sign over here. Here 2 meters is just a number, it's not a vector, you don't put a vector sign. These are correct, this one is correct, this one is correct, this one is correct. This one you don't have the units over there, so that's wrong.
Is it okay if you put units after the x hat and y hat?
That's fine. I mean, it gets confusing, but you have the units, that's fine. Okay, any other questions? Not about the quiz, but about the material we have. About the circular motion. Well, there is one question over there from the second seat. Yes, your question.
Okay, in a couple of previous pages we said that the radius was 0.
No, not the radius. I never said that the radius is 0. This one. It's the derivative of r squared is 0.
Oh, that's what I was going to ask. Because I thought when the radius was 0, the starting point of the velocity vector becomes the origin, like the center of the circle. So it becomes...
Well, the velocity, it cannot have a velocity in that case. Now, this is just the derivative of both sides. The derivative of the radius squared is 0. That's basically, the radius is not changing. The derivative of any quantity is proportional to its change. So if it is not changing, then the derivative is 0. So this is why we have the 0 over here. Other questions? Okay, of course, we can also have another means of proving that the acceleration vector is perpendicular to the velocity vector, just as we did with the proof that the velocity is perpendicular to the radius vector. So we know that velocity squared is equal to v0 squared, which is constant all the time. And we can just take the derivative of both sides. d by dt of v squared. Well, v squared is v0 squared, which doesn't change. The derivative is proportional to the change in a given quantity. If v0 squared is not changing, this should be 0. Well, you can also write it in terms of the components vx, vy, vz. If you take the derivative, you will get ax, ay, az. Or now I will just write it down. It's just like twice v scalar product dv by dt. This should be equal to 0. But this derivative, the rate of change of velocity, is nothing but what we call acceleration. So v dot a is equal to 0.
After that, we find that they are perpendicular. How can we define this direction?
Well, in this figure, you have the direction already. So, At this instant, we already know that, okay, this is the velocity vector. For this theta, this is the direction of acceleration, this is the delta v, so that is the direction of the acceleration also for that theta. If theta is not 0, they are not perpendicular to each other. But as theta goes to 0, they become more and more perpendicular. So this is the direction of delta v, and hence that is the direction of the acceleration. And that points towards the center. Now, how can we find it using this argument? Well, that will be part of your homework.
Always we are taking the derivatives. That's so classic. Everyone knows that. If we take the acceleration,
Okay.
derivative acceleration, what will happen?
Okay, that's a, okay. We started with position. We defined the change in the position to be the velocity. Then we defined the change in velocity. We called it acceleration. Why don't we define the change in acceleration? Wait, is that the question?
No, we are not sure.
Now, why don't we define a new concept called the change in acceleration? We will see when we study Newton's law that it is not necessary. We don't need it. Well, ask that question when we discuss the Newton's laws.
The product is zero, but neither velocity or acceleration magnitudes are zero. There is
True.
then different than zero, both in magnitude.
Their magnitudes are non-zero. We know that they are accelerating. We know that the velocity is non-zero because it's moving around. The speed is non-zero. Furthermore, since the velocity is changing its direction, we know that the acceleration doesn't have zero magnitude. We have non-zero acceleration. So, but their scalar product is zero, which just tells us that the v and a, they are perpendicular to each other. Okay, let's look at the trajectory once more. So we have this circle. Our object is going along that circle. Now let's put our coordinate axis now, so that we can talk about the components of the position. So let's choose this as our x-axis, this as our y-axis. We have, let's just assume at a given instant, my object is at that point. Its distance from the center is r, which is fixed. Now let's just assume that this is theta. We know that theta will be changing with time. So let's just say that at t equal to 0, my object is right over there. So what is theta as a function of time? If it is doing uniform circular motion, what is theta as a function of time? So let's first write theta in terms of this distance over there, the arc length. What is the relation between theta and L? It is L over R. What is L as a function of time? You say L over T. What can you say about L over T? It's V0. It's the speed, because it is the distance covered, that is L, in a time t. That's because at t equal to 0, my object is over here. At time t, it is over here, and it has covered the distance L. Now, the distance over the time is nothing but the speed. You see, it's not the displacement over time. The displacement over time will be the velocity vector, not the speed. So here it is the distance covered divided by the time, which gives us the speed. So L is nothing but V0 times t. And hence theta as a function of time is V0 over R times t. So we know how theta changes as a function of time. So how long does it take for the object to make one full rotation? How much? How long? So when it makes, yes, 2 pi r divided by V0, do you agree, disagree? How did you get that? Okay. Okay, so how long does one full revolution take? This is the question. Now, the most difficult part in this question is, what does this sentence mean mathematically? How can we write this sentence in a mathematical form? So what does one full revolution mean, again, mathematically? So what does one revolution mean?
2 pi angle or
Okay, 2 pi angle. So the object from t equal to 0, it starts at t equal to 0. After one full revolution, it comes back again to that point on the circle. So the angle it makes, this theta angle, just becomes the full angle, which is 2 pi. So this, if we call this time capital T, theta t is equal to 2 pi. So this is the expression of this question. So for which value of capital T is this satisfied? Now we already know what theta t is. We had calculated theta t in this particular problem. So we just put it over here. So we already know the value. This is V0 over R times T. So we can find this T. It is 2 pi R over V0, as your friend has pointed out. This is what we call the period of motion. So it is the time it takes to complete one full revolution, so that the motion will repeat itself after a period. Now, what is the position vector at this time? How can we write the position vector at this point? We already know the x and these are our x and y directions. We call this as theta. Do you agree? Well, what we do is we just draw these parallel lines to the y and the x-axis. This is the position of this point is nothing r cosine theta, and this position of this point is r sine theta. So it is r cosine theta in the x direction, r sine theta in the y direction. Now we already know what theta is. So R is, let's put capital R cosine of V0 over R t in the x direction plus sine of V0 over R t in the y direction. So we know the position vector as a function of time. Now, if you want to calculate the velocity vector and the acceleration vector, you just take the derivative of this one. So what is the velocity vector? Well, the velocity vector is nothing but the rate of change of the position, but the rate of change of position is nothing but the derivative of the position with respect to time. Well, how do you take the derivative? Well, x doesn't change as a function of time. It is always that vector pointing in that direction. Y doesn't change. It's again always the vector pointing in that direction. It doesn't change as the object is moving. So the derivatives of these ones will be 0. R is just a constant. Its derivative is also 0. So the only thing that depends on time are these cosines and sines, and we can just take the derivative. R times, what is the derivative of this cosine? Okay, minus sine of V0 over RT times V0 over R in the x direction plus cosine of V0 over RT times V0 over R in the y direction. So these R's I can also cancel. So the velocity vector is V0 minus sine V0 over RT in the x direction plus cosine V0 over RT in the y direction. So this is the velocity vector at an arbitrary time. Okay, this is not a vector. If you take the derivative once more, you get the expression for the acceleration vector. Can you show that this vector and this vector are perpendicular to each other? They are supposed to be perpendicular to each other, but can we check that? We can look at their scalar product. Now, if you look at their scalar product, remember, if you have two vectors, their scalar product is just multiply the x components, multiply the y components, multiply the z components, and sum them up. Now, the x component of this one is r times cosine. The x component of this one minus v0 times sine. So the product is v0 times r times sine times cosine with a minus sign. The y component of this one is r times sine. This one is v0 times cosine. It is plus r times v0 times sine and cosine. One with a minus, one with a plus. You sum them up. That gives you 0. And if you take the derivative once more, you get the acceleration vector, and you can actually show the direction. Now, if you have realized, for a single problem, we are just discussing various ways of obtaining the same result. One geometrical, one more mathematical, let's say. And you can just obtain the same result in different ways. And I would suggest you to learn at least 2 of the methods to obtain the same result. So that would allow you to test how well you understand the problem. Now, any questions on this one? Because I will just move on. So that's kind of everything I want to do about circular motion, at least for the time being. We know that if it is a uniform circular motion, we know that the acceleration is always pointing towards the center, and it has a constant magnitude. The speed is not changing. The speed is always, the velocity is always perpendicular to the position vector, and those are the critical things. Anything else you want to ask about circular motion? Okay. Now let's look at the projectile motion. In 2D and 3D. Now, if you remember when we were discussing the one-dimensional motion, we already said that if you stay close to the surface of the Earth, In that case, the acceleration of the object is more or less constant. It is always pointing towards the center of the Earth, and its magnitude is 9.8 meters per second squared, approximately. Of course, it changes from location to location, but more or less it's 9.8 meters per second squared. Now we will study the same problem, but this time not straight up, but in any direction. So let's assume that this is the surface. Here we have our object. So this is, let's say, the initial velocity of the object. So what will be the subsequent motion of the object? So that's our question. Now the acceleration vector will be pointing in this direction. This is our acceleration vector. Its magnitude will be equal to g, which is around 9.8 meters per second squared. So if we want to study this problem, first we have to choose some reference frame, some axis. How would you like to choose the axis and your reference frame? Okay, ground. Okay, so is it our reference point? It's our axis.
I think we should put the mass in the origin.
Okay, so you are saying that this should be our origin. Okay, that will simplify our life a bit. This is our origin. What should be the x and the y directions and the z direction?
I think y upwards negative.
Okay, y should be upward. Upward should be negative or positive?
Negative.
So,
For what time?
okay, so you want to have y to be in this direction. X is in which direction? X is towards the right, so that is in this direction. So this is our x direction. Okay, what about the z direction? In principle, it can be a three-dimensional motion. And this one. Well, conventionally, if you choose such x and y axes, the z axis will be pointing inside the screen. So this is how I will show it. So this will just mean that the z direction is pointing inside the screen. Now, you can just think of this as if you are looking at an arrow. If you look at from the back of an arrow, it will have this cross. If you are looking at the tip of the arrow, what you will see is you will see a dot, the tip of the arrow. So this is how we would show an axis that is moving in that direction, pointing straight towards you. Okay, so what is our acceleration vector in terms of the components? Now, because we already know that three-dimensional motion, if we just think in terms of the separate components, it just behaves like one-dimensional motion. Each component behaves like one-dimensional motion. So we would like firstly identify what are the components are. So what is our acceleration vectors? Once we have already chosen our axis, so what about the acceleration vector? So 9.8 in the plus y direction, meters per second squared. That is almost correct. Well, it's correct, let's say, but we usually, you see, if you look at this problem, okay, we know that G has this value, 9.8 meters per second squared, but there are all the other parameters which we do not know, their numerical value. We don't know what the initial speed is. We don't know what this angle is. We cannot put numerical values at this point for these parameters like theta and V0. So if you cannot just put all numerical values for all the parameters in your problem, you don't just put numerical values to the ones you know and keep the other ones symbolic. So if there are certain symbols that remain in your expression, you keep all the expressions symbolic. It is just G in the y direction. You don't put 9.8. because you will not be able to put numerical values to all the parameters. Okay, so what is our initial velocity? Vector.
Does our velocity have a z component?
How did you choose the x-axis? Ask him, he chose the x-axis. Does the velocity have a z component?
If while we are drawing, if it's xy plane, correct.
Okay. Well, you see,
You didn't show that it's that's correct.
well, on the screen, I don't really have a chance to show the V0 to have a z component or not. But remember, you have the freedom to choose the axis. Now, if you look at this V0 vector, okay, this is a natural choice for the y direction because the acceleration vector is pointing in that direction. Well, you could have as well chosen it to be upward, that's also fine. But, I mean, this vertical direction is a natural choice for one of the axes because the acceleration is pointing in that direction. Now, once you choose the y-axis, you can write V0 as a vector in the y direction plus another vector perpendicular to the y direction. Is that clear? So, this V0 vector will have a y component because you have already chosen the y-axis, plus the remaining part of V0 will not have any y component. But then you are free to choose the x and the y direction, x and the z direction. So a natural choice for one of the remaining two axes would be in the direction of what remains of V0. So V0, once you choose the y-axis, V0 will be, let's say V0y in the y direction plus whatever remains. It will be perpendicular to the y-axis. And you can choose the direction of this vector as your x-axis. You are choosing the axis. So that would be the choice I would make. That the V0 vector, what remains of the V0 vector once we separate this y component, should be the direction of the x-axis. So if we make that choice, in that case there is no z component. So I already eliminated the z component of V0. Whatever the initial V0 was, I can always choose my axis such that V0 only has the y and the x component and it doesn't have any z component. It's not a property of V0 itself, it's how I choose my coordinate axis that there is no z component. Is this clear? Well, you have these freedoms, like how to choose the coordinate axis. You are free to choose it whichever way you like. And you can choose it to eliminate to simplify the problem, eliminate some of the unknowns in your system. So that's what we are doing here. So we will choose the x and the y axis such that the V0 doesn't have any z component. Okay, V0 doesn't have any z component, so what are the components of V0? V0 sine theta, y hat, in which the x hat. Okay, do you agree? Now, y is minus. Now, why it's minus this time? Just imagine these two. Okay, this is the extension of my y-axis. We draw the perpendicular lines to the axis. Now, this length over here is V0 sine theta. It is the length. But you see, we had chosen the downside as the positive y-axis, but this point is on the negative y-axis. So we should add a minus sign over here. It's in the minus y hat direction. It's in the minus v0 sine y. Well, we had chosen the x and the y axis so that there is no z component left. Now, in this problem, I'm not studying a special type of initial velocity such that there is no z component. Any velocity, any initial velocity can be written in this form without any z component, because I am free to choose the x and the y axis. I choose the x and the y axis so that there is no z component. Now, another thing that you have to pay attention to is that I'm defining some positive sense to this angle theta. I'm defining this theta as the angle that V0 makes with the x-axis. I'm not defining it as the angle with the y-axis or not with the minus x-axis. It's the angle that the V0 vector makes with the positive x-axis. And theta is positive if you obtain it from the x-axis by a rotation in the counterclockwise sense. So all these angles, they are positive angles. All the other angles, they are negative angles. So with these conventions, this expression is valid even if my V0, initial V0 was pointing in this direction with this correct sign. If it is pointing in this direction, then theta would be a negative number. Sine of a negative angle is a negative number. So minus a negative number is positive number, so the y component is positive as it should be. Because if the vector is pointing in this direction, its y component is positive. So once I make these definitions, the conventions of how I define the positive angle, how I define the angles, this is valid even if theta is negative or larger than 90 degrees, etc. I don't need to add any more angles over there, any more signs over there. Okay, so we know the acceleration, we know the velocity. What about the initial position? Well, the object initial, we defined our origin to be the position of the object at the initial time, so the origin is at 0. The initial position of my object is at 0. Again, this is just, we are free to make this choice. So that kind of specifies all the initial conditions. Now, what about the position as a function of time? Now, we already know that the acceleration, it's constant. So it is equal to the average acceleration. Well, if it is the average acceleration, we know, we have already defined it. It is the change in the velocity divided by the time it takes. So independent of which time you assume, this is still true. This will be a constant. Now, let's assume the average acceleration between t equal to 0 and some later time t minus 0. This is our average acceleration. So v of t would be just v of at t equal to 0 plus a times t. The velocity at time t equal to 0 is v0 plus a times t. Now we can write this in terms of components. So we already know that v0 as a vector is v0 cosine. No. So this is our v0. It's a cosine theta in the x direction minus v0 sine theta in the y direction plus, well, the acceleration is just g in the y direction times t. So this is equal to v0 cosine theta in the x direction plus minus v0 sine theta plus gt in the y direction. So this is the velocity of my object as a function of time. So what does this tell us about the velocity? Now, in the pre-reports that were due last Sunday, some of you had still problems due to the add drops not being completed, the system not being synchronized. So I will not count this pre-report also for towards the final. So if you didn't do it, if you couldn't do it, you will not lose anything. But one of the questions that came was, okay, you are not supposed to write any equations. I will not refuse them. I will not deny them, but I would rather if you don't write any equations. So the question was, if we are not writing questions, what are we supposed to write over there? You see, here is our equation. So what is the story? What does it tell us? That is what you should write in your pre-reports. What do these equations tell me? Okay, it's not just a bunch of symbols, it is telling me something about the nature, about the events that's happening around us. Okay, the x, you see, x component, again, nature doesn't care about the x component. That was our choice. So what is the x component? How did we choose the x component? That is the horizontal component. That is the component perpendicular to the acceleration. So the horizontal component doesn't change. Okay, what else? So vertical component changes downwards. What else?
There is no one moment that acceleration up.
Acceleration is always there. Well, different components are independent of each other. Yeah, mainly these things. So there's a story behind this equation. There are some certain things that this equation is telling us. So you have to get used to interpreting these results. So okay, we have these formulas. If you didn't do any mathematical mistakes, we got some conclusion, but what does it tell us? Now, another thing which is kind of already in the first thing, the horizontal component doesn't change. It doesn't also change its direction, and hence there is no z component. Initially, there were no z component. Finally, there is no z component. There is never a z component. Now, let's look at in some more detail, especially the y component. So we know that the horizontal component doesn't change. But what about the y component of the velocity? So suppose we just throw this object you take your object, you throw it in some direction. So what is my y? X-axis in this case? It's over there. So this is the y component of the velocity. What remains in the velocity is pointing in that direction, so that's my x direction. And that's my y, x, y, and z is pointing in that direction. So in that particular example, that is V0 sin theta is positive. So does the y component of the velocity get smaller or larger with time, initially? Initially, at the moment that I throw my object, does the y component of the object its magnitude, does it get smaller or larger? It approaches 0. So the larger the time, the closer it becomes to 0, and eventually there will be a point at which it is exactly 0. So Vy, let's call it Tm, it is 0, and this happens when Tm be 0 sine theta over g. Now, up to this point, Vy was negative. So if Vy was negative, is our object going upward or downward? Vy is negative. Up or down? Downward, upward. What is the negative direction? Negative y direction. That is, you see, if you look at our definitions, always remember our definition. The positive y direction is pointing downward. If the Vy is negative, it means it's pointing upward. Negative y is pointing upward. So if Vy is negative, it means the object is going upward. So until this point, until this time, Tm, the choke is going upward. After this time, the velocity is, the y component of the velocity is positive, and hence it is going downward. So there's, at this point, at Tm, it is when it reaches the maximum height. Because until that time it was moving upward, after that time it is moving downward, so that is the maximum point. Now you should also note one thing, at least in our derivations. We always start from the definitions. For example, in this case, what we did, we first defined the problem. This is the definition of our problem. So somebody, you just either throw a chalk or kick a football, and there is a mass over here, you give it some initial velocity, that is the definition, or to experimental observations. This is our experimental observation, that the acceleration of an object moving close to the surface of the Earth is constant, almost constant, and has the value 9.8 meters per second squared. Here is again our definitions, definition of the average acceleration, definition of the velocity, and hence we obtain this velocity. So remember that we were discussing you should be always paying attention to the why questions. Now just writing a formula will not tell you the why. So that's why if you want to actually solve a problem, you always have to base your answers either to observations or to definitions. If your answer is anything besides either observation or definitions, then you are not really giving an answer. Of course, there's still the question, this doesn't end the why question. Definitions, you can define anything you like. These definitions, like you can define the change in the acceleration per unit time. It has a name, I forgot the name, it's never used, it's not necessary. It just doesn't survive the time. You can propose a new concept or propose a new definition. If it doesn't, if you want it to live for a long time, then people have to accept that definition and people have to think that it's useful. These definitions just turned out to be useful, but the change in acceleration didn't turn out to be useful. Why is the acceleration constant close to the surface of the Earth? Well, that is still a question that we are looking for answers for. But at least in all kinds of projectile motion, we can just answer all kinds of questions, all kinds of whys until this point. So if one day we can find an answer to this question, why is the gravitational acceleration constant close to the surface of the Earth or any mass, then we will have all the answer to all the why questions. Okay. Any questions before we go on? Now we will go for a break. If you don't have any questions, after the break we will study the trajectory, the position as a function of time, but do you have any questions before you go?